Okay, so let's get back to regular lecture now, and I'm recording for YouTube, so you'll be able to review this part of today's lecture in YouTube as soon as I upload it. A couple things I want to review with you about what we just did. If we have self-paced polling on exam X on Tuesday, it'll be similar to this, except you'll be working off the page, all right? And it is usually the last page of the exam. Now, I might have some multiple choice and some calculations. It could be, I could ask you for a word, you know. Each of the three questions that we just did, I could have one of each of those on the clicking part of the test. Question?
Yes. What would you say is the most important topic to study this student?
I'll talk about that later. We've already talked about stuff like that. Let me talk about this. This is more important. Now, this is a page from exam 2 from my physical science class last spring. All right, and this is the clicker page. And we were studying thermal physics, so I had a picture of a polar bear at the North Pole and stuff. But in general, my exams will look something like this. The first thing you'll see is the cover page. All right, and it will look like this. Now, this is the cover page for exam 2 in physical science. We are studying gravitational energy and kinetic energy and heat energy. But you'll have, at the top, your name and your PID, the date, and so forth, first and last name. Then a little bit of directions. You can see here I've got a table of some thermal constants. And by the way, if I ask you to work with some numbers, usually I will give them to you in the test. In other words, something from which you do a calculation. Now, these are the thermal constants associated with water and carbon fiber and magnesium. And that was part of the test that we had last spring, exam 2. Here's the first page of that test. Now, this is not astronomy stuff, but it does show you the layout and kind of how the formulas will work for us. Now, here is a close-up. If you look at the first two items, kinetic energy and gravitational potential energy, you'll see above there a bunch of formulas, okay? And one of them is the correct answer for each of the first two items, all right? Now, those are physical science, Lib 21 formulas. We have a few formulas different for astronomy, but it'll look something like this, all right? And I mentioned this last time. So, as I said, you do not consider your task to memorize. Your task is to recognize. Because there's the formula right up there. You have to recognize the concept that goes with it. So that's a slightly easier task than just memorizing. All right? And then below that starts the true, false, and everything else like that. All right? Now, here's the clicker page. All right? And the clicker page, there's the top of it. That's the instructions that you just looked at on the screen. And these will be at the top of the clicker page, same as today. All right? And then further down the page, you'll see the actual questions. All right, so here they are. Number 1, a boxcar calculation. Number 2, thermal energy calculation. Each of those was 2 points. And so that test I had 46 Scantron items and 2 clicker items, each of them 2 points each, total of 50. And what is your name again?
Me.
Yeah. Anne. Anne was asking, why do we have to do it in clicking? The answer is that students that tackled both of these questions and calculated the momentum state of a boxcar and a thermal energy budget in number 2. If they made a slight mistake, I could spot it because what I do, all the answers that you type in, the very first thing you send and then the very last thing that you send, in case you change it, I look at the very last thing that you send, and I look at it closely, and if it's right, if the answer is 2.7, and you send in the number 2.7, then I don't have to look at it, and it gets the points. But if you put in 2.68, I might say, all right. Or I might say, nope, I asked for one decimal point. I'll only give partial credit for that. All right, so it just depends on how it should be graded. And so that's why this gives an advantage to me, because it lets me give you a little bit of finesse in the grading. And I think everybody would like to have partial credit when possible, even if they don't get it right, because if you don't get it right exactly, Scantron marks you wrong, but not clicking. I can mark it partial credit, or I can even mark it correct. Because there's an infinite way of screwing things up. But since I'm a human and not a machine, I can interpret your screw-ups as a good answer. All right. And just a final comment, remember to hit the send key after each answer, and that'll be good. All right. Now, last time we talked about the other two laws of planetary motion. We already had this one. The elliptical orbits law. We then talked about this one, the equal areas law, also concerning elliptical orbits. And finally, we talked about the third law, which is the really important one. In the solar system, we have this version here. P squared equals a to the third. Capital P being the period of the orbit. In other words, 1 year if it's Earth. A little bit less than that if it's Venus. A little bit more than that if it's Mars. And as we're going to talk about today in connection to Sir Isaac Newton and his law of universal gravitation, the general formula for any pair of gravitating objects, binary stars, or a giant star and a black hole, or a black hole and a bunch of other stars, yeah, we would use this version. And this version works anywhere in the galaxy. If you can get measurements of the period, and if you can get measurements of the semi-major axis A, whether it be in light years or astronomical units or any other distance measurement. If we do that, we can figure out the mass of M1 and M2, both of those objects. Now, let's keep going into 3.3, and I really, really love this big quotation, so let's just look at it. Just make a note. Once Newton boldly hypothesized, that's the beginning of a paragraph in 3.3. And here's the full paragraph. Once Newton boldly hypothesized that there is a universal attraction among all bodies everywhere in space. So in other words, the Andromeda Galaxy and your left earlobe are interacting gravitationally. You may not notice it, but I mean, it's not a very strong force, but theoretically, to Sir Isaac Newton, yes, everything attracts everything else in the universe. Once he had hypothesized that, he had to determine the exact nature of the attraction. In other words, he had to figure out the formula. The precise mathematical description of that gravitational force had to dictate, A, that the planets move exactly as Kepler had described them to move, as expressed in Kepler's three laws, and B, that the gravitational force had to predict the correct behavior of falling bodies on Earth, terrestrial freefall, as observed and described by Galileo. So the work of Galileo, prior to Sir Isaac Newton, and the work of Kepler, building on the work of Copernicus and Tycho Brahe, that all had to square with Sir Isaac Newton's hypothesis. Let me repeat that. In any scientific endeavor, if you propose a theory, it has to be consistent and square with all the observations prior to that. So in this context, Galileo and Kepler. All right? And then the last sentence reads, how must the force of gravity depend on distance in order for those conditions to be met? In other words, in order for Kepler and Galileo to remain squared away in the law of universal gravitation. And the answer is this formula. Here it is. And if you read 3.3, you know that this is the formula for the law of universal gravitation between mass 1 and mass 2. Now, I chose to display this with the Earth and the Moon. Now, the distance is a little bit out of proportion, but the diameters of these two spheres are in proportion. The yellow dashed line is the distance, center to center. So Sir Isaac Newton said, if you want to calculate the force, F, you got to know how many kilograms for the Moon, how many kilograms for Earth, and you got to know the distance. And then you got to square the distance and put that in the denominator. And then he said, because the square, so if you think about it, M1, M2, that's kilograms squared, right? In the numerator. In the denominator, square of a distance, that's meter squared. Kilograms squared per meter squared is not a metric unit of force, and it is definitely not any unit of force. Did you know that in the English system of Sir Isaac Newton's day, the unit of force, and still is actually, the pound? You know, when you weigh yourself on the scale, 102 pounds, or whatever it happens to be, that's actually measuring, that's the number of the size of the force that's pushing you up and keeping you stable. You're pushing down with that much force, the springs in the scale are pushing up with that force, and that's what reads out on the dial in pounds. In the metric system, it's a unit called newtons, which is kilogram meter per second squared. And because because kilogram squared per meter squared is not a unit of force, Sir Isaac Newton had to use the conversion constant, or the conversion factor, capital G. That's known as Newton's constant, also the universal gravitational constant. Right? Now, in terms of the Moon and the and Earth, I've just changed the subscript. The first mass is a circle with a plus sign in it. That's the astronomical symbol for Earth. And then I couldn't find a symbol for the Moon, which is usually a little crescent, or just the word moon. So I typed in the letter L for lunar. The lunar mass, that's the second mass, up in the numerator. And then the square of the distance is down below there. Now, Sir Isaac Newton worked all the calculus and all the trig out. And it all squared up with Kepler's three laws. In fact, it was a major victory for Sir Isaac Newton to have done that. Here's the way the forces will compose themselves. The Earth will feel a force toward the Moon. So that's this arrow down here. All right? This arrow with its tail at the center of Earth represents the tug that the Moon exerts on Earth itself. A similar arrow could be attached to every gram of water in the oceans of Earth. The sum of all those forces in all the grams in the water of the oceans of Earth would lead to an effect that many of you have seen, tides. Okay? The Earth itself is a big rock. It's pretty rigid. Not perfectly rigid, but really rigid. But water is not. So water, if it's a little bit closer on this near side of the Earth, that water will get just a little bit bigger tug than the Earth itself. And because of that, the water on the near side of the Earth tends to pile up. The water tends to head towards that side of the Earth. And similarly, the water over here on the far side of the Earth doesn't get as big a force as anything else. It's kind of the shrimpy force back there. Not by much, but enough to produce tides. High water directly or pretty close to directly beneath the moon, and then high water on the other side of the planet. And then up here and down here, those would be low tides. So that's how the tides work. And Sir Isaac Newton's the one that figured it out. And how come the arrows are the same size? You might think, well, how come the moon and the Earth, they have the same size forces? The reason for that is Sir Isaac Newton's third law. His third law of motion in general, which, this is the famous one, you've heard it. For every action, there's an equal but opposite reaction. Yeah, this is what he was talking about. When he wrote his famous book, The Principia, he started out thinking about everything. And I read his book. I didn't read it in Latin, in the original, but I read the English translation of it. And he was thinking of, you can read it, he was thinking about gravity the whole time, from the page 1. And so all of his laws of motion were directed towards getting to the law of universal gravitation. It's unbelievable. So once he boldly hypothesized that force law, here it is again up here at the top right, all the other laws fell into place. And here's another pull quote. With such a force and the laws of motion, his 3 laws of motion, Newton was able to show mathematically, using calculus and trig at the wazoo, that the only orbits permitted were exactly those described by Kepler's 3 laws. So he figured out why Kepler was able to discover those laws. Those laws existed before Kepler, and Kepler pieced them together and kind of discovered them. And Sir Isaac Newton said, yeah, if it's really GM1, M2 over R squared, then yeah, you're going to get elliptical orbits, but the sun has to be at one of the focus points. All right, that's the first law. Second law, sweeping out equal areas in equal times. Yeah, Sir Isaac Newton figured that one out too. If it's really GM1, M2 over R squared, then yeah, equal area laws has to apply. He got that one. And most important of all, the third law. P squared equals 4 pi squared over the quotient, over the denominator G, and the sum M1 plus M2, all times the quantity a to the third. And this one down here, the reformulation of the third law, in its most general form, is the one that we're going to be talking about today and filling in all the specs for it so that we can understand why it is so important for an astronomer. Because Newton's third law in this form, Kepler's third law in this form, is what allows us to know the mass of any object in the universe if we can measure the semi-major axis of its orbit and time it. So if we can time it, for a few years or a few days, we can measure the mass of Jupiter with this. We time the moons. Galileo 400 years ago saw the moons, not a problem. And if he had been able to figure out Newton's law of universal gravitation, he would have been able to compute the mass of Jupiter. All right. Now, final note on this from 3.3, we're going to dip back into 3.3 one more time next Thursday when we start talking about the outer planets. And yes, there will be some homework next week after the exam. So lovely. So much fun. You won't get the week off. Basically, because we had the hurricanes. All right. Now, I want to push forward to 19.2, but first a question.
Yeah, I know that
The point of G in the equation is to convert from a pair of measurements of mass and the square of a distance measurement into a force measurement. And here's one, and I don't know if I mentioned it in this class or the morning class. There is, in fact, we did mention it. When you convert from Celsius to Fahrenheit, there's like a factor of 5/9 or 9/5 going the other way. Same thing, or very similar. You know, to go in one direction, you use 5/9. To go in the other direction, you do 9/5. And then you got to subtract 32 or add 32. You remember doing that in like 5th grade? No, you don't? Okay, well, you probably did it in 5th or 7th grade or something and forgot about it. But yeah, that's what it's like. It's a conversion factor. Question?
Are we using 9.81 or
G?
for G? Yeah, because I know it's centrifuge is different.
This is not the G of the free fall G. Yeah, this is Newton's constant. This is the universal gravitation. You know what G is? G is G times the mass of the Earth divided by the square of Earth's radius. And all those three things, that's equal to 9.81 meters per second squared. G is the universal constant, no matter what planet, star, or galaxy you're thinking of. But all the other stuff, you know, the P and the A and the masses and stuff are different. So. All right, let's go into 19.2. We're going to talk about how to use trig, triangulation, and the idea of parallax to measure the distance to stars, planets, and other things that we could see out in the universe. Now, in general, when you're working with a right triangle, if you can measure one of the acute angles and one side, whether it's the hypotenuse or one of the two perpendicular sides, if you get any one of those three sides in an acute angle, and then of course it's a right triangle, so one of the other angles is a 90-degree angle, okay? Then you can get the lengths of the other sides. You get one side in an angle, ching, you've got all the other sides. All right? And, you know, sometimes you have to use trig formulas. Raise your hand if you had trig in like high school or up here at UCF. Okay. And if you remember, for those of you that had trig class, sine, cosine, and tangent, big tables and stuff, yeah. Now, we're not going to be doing any of that because we're not supposed to in this class. About the most trig that we're going to do is the Pythagorean theorem. A squared plus B squared equals C squared. By the way, mental IQ test question, not on the iClickers though. What would you call a pot of water boiling on top of Mount Everest? A hypotenuse. High pot in use. Get it? Get it? All right, here's another one. Here's another ultra cool math joke. What did the acorn say when he grew up?
Acorn.
Geometry. Geometry. That's right. Yeah, those are the only two math. You know, some people know a million math jokes. Those are the only two I know. All right, so here's what terrestrial surveyors do if they don't have their laser rangefinder, which is what they use nowadays. They have to triangulate things in. And this is the way that Abraham Lincoln, did you know that when he was a young man, he was a surveyor? He measured off parcels of ground out there in the land of Lincoln in Illinois. So you basically, if you step off the baseline, you know, so many yards of baseline, and then you measure the tilt angles. You know, you sight in on that tree on the other side of the creek from two different points, opposite ends of the baseline. If you do that and measure your angles, and then if you know your trig tables and stuff, you can figure the distance across the stream. No problema. It basically boils down to a bunch of Pythagorean theorem action. Now, we're not going to have to do that because the parallax effect that we will use in astronomy is a little bit cinchier than using trig tables and Pythagorean theorem and stuff. All right, now, to understand that, the parallax effect, I'm going to point out another nice quote from 19.2. To see what we mean by parallax, take a pen, or if you want, your thumb, and extend your arm. And it says hold it a few inches in front of your face. But go ahead and do this, okay? Take your arm, your right arm or your left arm, and close one eye, and then use your thumb to like cover up like one of the speakers or maybe one of these lights up here. And I'm going to cover up the exit light. Okay, so keep one eye closed and use your thumb to cover it up. Now open the other eye and close the first eye, and you'll see that the light or whatever it was you were covering up, it moves. Or it appears to move. It's still the same place. But what you're getting, that's parallax. And the reason for that is that your baseline is a few centimeters from eyeball to eyeball. And that is enough for you to perceive the depth, and your depth perception is based on that. And if you do this with your thumb, that gives you the parallax effect. Now, in astronomy, it looks like this. This is figure 3 from section 19.2. And this is really, really simplified. Now, here's your target over here where this white arrow is. And if you look carefully at this diagram, take a look at it. Is that red circle, the target with the white arrow, is that a star? Why not? Why isn't that a star? Why is it impossible for that to be a star? Look at the picture. Because the sun is what?
Because the sun is like the only star in the sky.
Well, that's part of the answer. The sun is the only star. And is that point, that red point, the target point, where is that in relation to Earth? It's further away from the sun. But how many, what do you see?
So it doesn't move and stay in the same place.
No, that's not it. That's the parallax measurement technique. But just talking about this point, even before you do that, what's wrong about saying that this is a star? What's that?
It's like directly aligned with another star?
No, it's not. It's not that it's directly aligned with the sun or anything else. What?
Would you not be able to see the one dot, like, inside that room?
No. What do you think?
Like, as you can see from the diagram, you have sky seen from B and sky seen from A. On either point of the orbits, the distance that changes when you see it from either two orbits is too great. Like, for instance,
You're barking up the right tree, but that's not why this can't be a star. Because there are star systems that would do this. Yes.
Its size.
Not its size. Look at it. The distance from the sun is 1 astronomical unit. It's about 5 astronomical units out to Jupiter, if I recall correctly. This thing is definitely not thousands of astronomical units away. It's just a few AUs away from the sun. So that's maybe a planet, but it's definitely not a star. None of our stars are so close that we have clear, nice, right triangles like that. So this diagram is exaggerated in the sense, or the target point is chosen fairly close in. Now, we wouldn't usually use a parallax for measuring something inside the solar system. This red dot is in the solar system, somewhere out by Jupiter, according to the sketch. All right, now we wouldn't use parallax for that, but the triangles are the same. For a real star, the parallax triangles are much, much more slivery. These ones, yeah, that angle, P, see that angle P up there? Okay. See the dashed line that goes right straight from the target point to the sun? That forms a right triangle. Okay. And the slanted lines that go from point B to the star, to the red dot, and from point A to the red dot, those are the hypotenuses of two identical right triangles. All right? And then the baseline from point A to point B, that's your baseline. Remember this picture we had over here? This picture? The baseline from one observation point to the other was maybe a few yards in this one. Now over here, for this diagram, your baseline is 2 astronomical units. So B might be like June, and point A would be like December. All right? All right, so make a note of that. Now, what you do when you're doing parallax to a star, you measure basically 2 different aiming angles. Because June and December, you've got to look at that target, you've got to tilt your telescope just slightly differently. And this one's fairly close in this diagram, but a real star, the amount of tilt, the difference in the tilt angles is really small. Not even a parallax, not even 1 second of arc. Right? It's usually even smaller than a second of arc. All right, so that angle P up there, see that one? All right, the triangle from A to B and out to the target and then back to A, that triangle, if you split it in half with the dashed line, the slivery angle up there is P, and that's the parallax angle. That's the one that we want to measure using a really good telescope and a really good protractor. All right? And Tycho Brahe was trying to get parallax. Everybody was trying to get it, but nobody could get it till about the 1800s, as you read about in chapter 7 and 19.2. So for very tiny parallax angles, the trig formula is really easy. And this is a formula for the test on Tuesday. Here it is. The distance in parsecs is 1 over the size of that angle. Right? So, and because as Earth travels from one side of the orbit to the other, it graciously provides us with a baseline of 2 astronomical units, about 300 million miles, or 300 million kilometers, which is nice. You know, so we can triangulate. If we can get, for instance, a parallax angle of 0.10 seconds of arc. Go ahead and write that down, because you're going to do a clicker question here in a minute with a numeric answer using this formula. If that's your very small angle, very small parallax angle, so June you measure it in one direction, and then in December you measure it again, and it's just 0.10 seconds of arc away from your original aim point, then you've measured the parallax, and the distance is the reciprocal of that. So what is 1 over 0.1? That's equal to 10. Get your calculator out and verify that. And in your next clicker question, go ahead and turn your clickers back on if they've turned off, and hit the refresh button. You should have Go Nitro now. And we're going to do a numeric question here. And you're going to use this. You're going to do a regular calculation with this formula. And this is an example. Now here's another quote from 19.2. How far away would a star have to be in light years or astronomical units to have a parallax angle of exactly 1 arc second? The answer to that turns out to be, and go ahead and write this number down, 206,265 astronomical units. So multiply the distance from Earth to the Sun by 206,265, and anything at that distance from June to December, you'd measure 1 exact second of arc, which is teeny. But a good telescope, you can do it. And we could even get smaller parallaxes than that. In light years, that's the same as 3.26 light years. All right? Or 3.3 if you round it off. Question?
So we would divide or multiply?
Yeah. You take the parallax angle, like 0.1 arc seconds, and just go 1 over. 1 over 0.1. And that gives you the distance in parsecs. So parsec is a distance unit that many astronomers use. It's equivalent to 3.26 light years or 206,265 AUs. Now, to measure a distance to a star, we don't usually use AUs. But we do use light years, okay? And we do use it, shorthand parsec, and it's basically 1 over whatever the parallax angle is measured to be. All right? So that's how we use parsecs in this. All right, question?
Why did they use parsecs as a number that wasn't even? Why wouldn't they make it something that was like 4 letters away? Or like 300 Why did it just 3.2?
You have to ask the ancient Sumerians that divided things up in 6s and 12s and 60s. Yeah, it traces because it's a second, so it all traces back, 6,000 years. All right, here's your question. Go ahead and start on. Pull down the menu, numeric, and go, and just close that. Okay, here's your question. The parallax angle for Series A and Series B, 0.38. All right, now here's your distance formula. 0.38.
I can't call 038.
Dude, I just picked it up on Siri. What? Sorry, Thomas, I can't call 038. Nice. Nice to know Siri's on the job. Yeah, go ahead and type in your answer to the nearest 0.1 parsec. Right? So if your answer, so this is how the exams are going to be written. I'll always tell you how to, and don't type in PC, just give me a number. So the numeric part of your answer, round it off to 1 decimal point. Okay? So if your answer is 4.587, type in 4.6 and then hit the send key. Question?
Turn it off or turn it back on?
Hit the refresh key. And it'll start you on the number 1, and then you just go up or down from there. Yeah. What's that?
It's right after
Well, they know that that it's 206,265 AUs, and every AU is 500 light seconds. So then that tells you, that you've got 3.26 years worth of light travel. Yeah. So once you get, you're a physics major, right? Yeah. So this is a small angle approximation of the tangent. Yeah. So this is like tan theta equals theta. And then the other thing is, opposite over adjacent. Opposite over adjacent, that's definition of tangent. And then small angle approximation tangent theta is equal to theta. So that's basically what this is. Yeah, that's what this is. And then they cross multiply, and so the adjacent is equal to opposite divided by theta. So yeah, so that's how that works. Yeah. Yeah. But we're not allowed to talk about trig in this class, so. All right, so do your calculation carefully. Can you see what? You guys are doing good. 30 seconds. Get it? Where's the decimal? Is it below the zero or above the zero?
I think it's arrow.
Below the zero? And it's really hard to see. I wish it was easier to see you guys, but we can't really control the lights in here very well, so. I guess if I do numeric questions on the test, I'll have to make them whole number answers. So you don't have to use this. The decimal point is such a pain in the... Yeah, it's right next to the previous number. It's a pain. 10 seconds. 10, 9, 8, 7, 6, and 5. You got it? 4, 3, 2, 1. 0. Switch to, go ahead and maximize that. And switch to the desktop. And most of you answered 2.6, which is good. Can you drag the slider down a little bit and see if we can look at some of the other answers?
I don't think there are anymore.
There are, but
Oh.
yeah, it's tricky to get them. It's hard to get that thing to move. See, look. Hold on. Look at this. All right, so now this 2.63. Technically, that I could mark that incorrect if I wanted to, but a Scantron machine would mark that wrong. But I might give it partial credit or even full credit, depending on how nice of a guy I feel like being. Same with, I don't know about this last guy with 8 digits. I mean, that's a little. I might not give him full credit just because it paralyzes my eyes for reading such a long answer. Anyways, so you can see that iClicker records everything that you've got, and I can look at it in a spreadsheet. It works really nicely. Switch back to the regular display, please. Thank you. All right, so here's your answer. And hey, you guys, how many light years is that? It's 3.26 times 8.6, or 3.26 times 2.6, total of 8.6 light years. Now, almost done. Some astronomers work in parsecs, kiloparsecs, megaparsecs to galaxies. Some light years, kilo light years, mega light years out to galaxies. So here's the upshot for us. If you can get parallax, and if you know the baseline, you can calculate the actual size of an orbit, just like this one. And then Kepler's law will get you the mass. Now, we've already looked at that. For Sagittarius A star, yeah, we got the mass, 3.7 million times the mass of the sun. And we know that the semi-major axis for star S2, 5.5 light days. Yeah, we could do that because we had a baseline and a parallax. We got it. We bagged it. Matter of fact, we even know how big the event horizon is. Now, before we dismiss, I want to speak for a few minutes about the exam. If you are smart, if you are still here in the room, and you didn't leave early, like I saw a few people going, you're going to know something handy. Specifically, well, let me just ask you this. If I did put this diagram, this is Series A and Series B, timed, and notice that there's a little measuring scale down there on the bottom? Yeah. If I were to put that on the cover page, there's a guy that he took off. He was asking me, what's the most important thing? And he left before he gets the answer. My wonderful students, I put a lot of importance on this diagram. Think of all the basic questions you could ask about this diagram. Think of all the different formulas that we could, I think almost every formula that we have, we only have a few, could be applied to this diagram or to a table. Think of a table. I could give you the years and the distances in a table, like right alongside the diagram itself. Think of the brain burner. Now, there will be one or two on there. I don't want my exam to be easy to ace. I want you to work for it. You can ace it, but you got to work for it. But this diagram alone, I could ask a 50-question test on Series A and Series B alone. Matter of fact, I could make every test this semester just about on Series A and Series B, except for planets. We don't have any planets for those two stars. Anyway, I was in office hours. I know you guys are antsy to get out. One more thing. I was in office hours talking with a student yesterday, and the student was asking me, well, Dr. B, how can I get ready? I'm a little bit worried about these formulas. Now, you know that you don't have to memorize them. But I came up with an idea as we were there talking. Every formula, and we've only got 3 or 4, I think, you could write it down, and then for every formula, write one sentence how Dr. B described this formula. And then the second sentence about the same formula, how would an astronomer use this formula? Now, we've got 3 or 4 formulas. If you can do that, a couple sentences for each, and not everybody's going to write the same sentence, but it could express the same facts. If you can do that, that will really, really help you, A, recognize the formulas and the matching, and then B, use the formulas efficiently and quickly on the test itself. And when you do that, you'll be able to calculate and calculate with confidence. And when you can do that, you're on your way to crushing my exam. All right, you're dismissed, 2:49. I'll see you on Tuesday.
Do you need to, is this already automatically saved and all that? You don't need to save it?
No, I'll show you what to do. You can X out of the, okay. Now X out of that, okay. And now you can eject. No, in the,
Oh, eject.
yeah. So right click that, and then
Cool.
and that'll be good. All right, and you can detach that. If I can get my cursor back.